data science team at Barclays. And part of all this presentation is perhaps to give you a bit of an idea of what that data science thing means, because it underpins a lot of the kind of digital propositions that people are talking about at the moment, and yet people have lots of different ideas about it. So this is sort of maybe a little bit of my idea about how we work and the kind of things we do. And hopefully, if you're technical and mathematical, you'll get something out of this, because there's some sort of interesting ways of kind of changing the way you think about a kind of fairly common sort of data set in order to turn it into one that's going to give you kind of recommendations or personalization or what I call a similarity metric. But if you're not a technical person, hopefully what you'll get out of it is this is the kind of thing that this data science person that hopefully some of you have heard about is doing, and the kind of tools they're using. Now, I kind of live in my own little world a lot at Barclays, and so if I mention any kind of terms or software or tools and I forget to explain what they are, just shout, right? I'm very happy to tell you. I'm not trying to bamboozle you. I just, I think in these terms every day, so I'm sort of really used to it. So, recommendations. So when we think about personalization, in fact, I call it recommendation, it's about personalization. They're all sort of the same thing. I think in terms of similarity, in what way is one thing similar to another? And this is used in all the kind of recommendation applications you've sort of seen in sort of Amazon book recommendation or whatever. They're sort of saying, in what sense is one person like another or one book like another? And in that sense, can you map between books and people depending upon what you know? So there's a number of sort of different ways of thinking about similarity. So, how is Tesco similar to Asda? Or how is Tesco in Bristol similar to Asda maybe in somewhere else, Bath or Newcastle upon Tyne? Or, how can you think about similarity between these two things? Or how is Tesco in Bristol similar to kind of like the Bristol Angling Centre? There is such a thing. I found it on our thing. So, similar sort of plays, but very different kind of thing. And if you're trying to think about the similarity between in this case, shops, you might want to think about, well, what does that actually mean? So generally, so the way we thought about this, I think this is an interesting problem, right? I hope some of you think this is an interesting problem too. But there's this kind of philosophical idea of similarity. And so our first sort of step in thinking about similarity is we've assumed that the similarity of two businesses can be measured by whether they share customers in some sort of sense. So if two shops in Bristol shared exactly the same customers, then they would probably be very similar sorts of shops. But this can we go beyond that to understand perhaps how a number of different shops sharing a number of different subsets of customers can in some sense be more or less similar. Not is this exactly the same, but if it's not exactly the same and if it's not completely and utterly different, in what sense is it the same, and in what sense can you kind of rank businesses in terms of how similar they are? Is this going in the right direction? If this is really bad, I'll talk about something else. Okay. So look, this is the kind of data set you'd expect us to have at Barclays. It's transactions, right? You've got buyers, you've got sellers, you've got a timestamp, they bought it at this time of day, and the amount they spent. I mean, you can imagine we've got all sorts of extra data. Most of it's not very good, but we've got a lot of these. And this is billions of rows, right? Tens of millions of these guys, millions of these guys, billions of rows. So it's a big data problem. To those of you who know about big data, right? Lots of this stuff. But actually, you probably all have got some sort of data. If you're dealing with data, you've got some sort of data like this. Person and book, in Amazon's case, right? I was talking to some hedge fund guys, similar sort of thing to this, and they've kind of got entity and maybe financial instrument they're investing in or something, right? You nearly always, if you've got this kind of list of people, right, or things, you're relating one thing to another. You're going to have a long list of A and B. And in this case, people shopping at shops. So this is like really ordinary stuff, right? And in some sense, you know, well, how is that going to help me about similarity? Okay, so I'm interested in how people and shops fit together, or shops and shops fit together. Or conventionally, this is the only bit of mathematics. Or no, this is the only bit of kind of formal symbolism we've got. There's this thing called cosine similarity, and anyone who knows about the dot product knows that you could take all your customers, whether they shop at a pair, right, Tesco and Asda, but it could be any pair of shops, encode yeses as ones, nos as zeros, you get two vectors coming out, and if you do the dot product, that's the same as this thing, right, which is the length of A and the length of B, and the cosine of the thing between. What does it mean? Forget all of that. Forget all of that, right? What it means is that you can tell how related A is to B by seeing how if orthogonal to B, if you project down, imagine I was shining a light up here, right? And shining a light on A, and A would cast a shadow this long along B, right? And the more like A, B is, remember this is in lots of dimensions, right? But imagine we just had 2 dimensions. The more like A, it's more like B, A is, the more likely that this shadow would exactly fit one on top of the other, right? That's all cosine similarity is. And if it's orthogonal, right? So if it's at right angles, you shine your light down, and it would only be a spot of no length at all. That's how a lot of similarity metrics work. And once you then have this similarity metric, you can say A is really like B, it's almost 1, but C is almost completely unlike B, it's almost 0, right? Then you are sort of laughing, right? Because you can rank how, you know, this one's really, you know, this person is really like this person, so I'll recommend what the other person has done, or this person's really unlike this person, or this shop is really like it, right? You can rank them. That's what it's all about. But you kind of notice here, the first 2 things is you can only ever compare 2 things, and the data between those 2 things never seems to go kind of beyond that. So I can kind of look at how like Tesco is to Asda by the customers they share, but what about customers that they don't share? So I want to know how like Tesco Asda is, but I want to include the information from people who shop at Tesco but don't shop at Asda, but shop at Waitrose, and people at Waitrose shop at Asda, right? There's some kind of information there that kind of propagates through all this, right? And did that make sense to you, right? It just because there's information out there that we can include that isn't just included in that pair when we want to be comparing those 2 things. It's kind of limited in that sense. But this is how most of them work, in some sort of sense, right? They then put it through some fancy algorithm, right? But that's essentially what they care about, how like one thing is another. So this is another one. I'm going to go through it pretty quick. I said there was no symbolism. Yeah, it's sort of symbolism, right? But the other main way they do these things is, again, they kind of encode the same sort of thing in your matrix and all of that. And then they decompose a big matrix of yeses and nos, right? And it can go much beyond Tesco and Asda, this one. This one isn't related to pairs. And it says, I'm going to decompose it into 2 matrices, which when they multiply together, give you as close to this answer as possible. So you've got some kind of optimization, right? And the 2 matrices it turns into, you don't need to know about it. You can look up matrix factorization or alternative least squares or something if you're interested. But it's basically, it's all your customers and the kind of preferences of those customers, right? So whether they like this kind of shop or that kind of shop. In fact, each of the columns, each of these preferences do not naturally come, you wouldn't be able to look at them and necessarily say these people like big things or these people like yellow things, right? There's some kind of maths going on, right, that gives you some sort of abstract set of preferences. But these are roughly the preferences of each customer, and then this is how those preferences map onto the attributes of each business, right? You multiply them 2 together, and you can find how customers map to businesses. The interesting thing about this is that it's used way beyond personalization. So it's used in something called topic modeling. So if you've ever been interested in how you might build algorithms to read text and understand text, in fact, perhaps take a whole load of documents and say what the document is about automatically. It's the same thing, actually. It's still these ones and zeros, right? But it's you know, this book is about the Russian Revolution, and this book is about flower arranging, right? You'd use the same sort of topic modeling, again, large thing. But again, the problem with this is that it doesn't explicitly understand how relationships work between not immediately connected things. And it also smooths them out. This turns out to be okay, quite good at getting most of the way there, but not really good at getting the fine detail of personalization. And for all you marketing guys out there, I'm going to give you a bit of, bring you back into it because we lost you with all the maths. That the economics of personalization are that the value is in the last couple of percent, right? This isn't an 80-20 rule thing where if you just get most of it done, it's fine. The value in personalization is really personalizing, right? So this is actually not very good at all, because although it gets you 80% of the way there very easily, it doesn't get that last little bit of personalization where you really feel like someone knows what you want. So it's kind of not ideal. So we set ourselves a challenge, sort of interested in this. Why are we interested in the bank? Well, we're partly interested in personalization, but we're also interested in kind of trying to work out the DNA of our customers, right? In some sense, we're using the list of shops, not just the shops that they shop at, but the shops that they probably would shop at if they, their latent preferences, as some sort of DNA of who they are in order for us to then think about maybe the products they might want to buy. Okay. Graphs. Who's heard of graphs? Networks, social networks, graphs, all that sort of stuff. So it's all the rage, and it's very exciting, apparently. So this is the same sort of thing you've seen before, except instead of having individual names, I call them customer ID. But it's the same thing, right? Someone buying from a shop, a certain amount, timestamp. And I've ignored the first and the last column. And what you can think about is, instead of thinking about this as a long list of transactions, right? Shopping trips, people going out, buying stuff, coming back, buying another thing, maybe at the same time. Actually, the time thing is interesting, but no time for that. What you've got here is a graph of relationships between people and shops, and between shops and people. Right? So in some sense, this has you can think of this as having the same sort of structure as, I don't know, Facebook or something. You can think about them with the same sort of relationships that propagate through the graph. So here's a picture of that. I didn't put on the ones and the twos, but there's someone who shops at Tesco and Asda. That's number one. Who's 3 shops at Tesco, Boots, and I think he's this guy. So, you've got this is a graphical representation of that. And you can see that there are shops and there are people, and you can see that in some sense there must be some sort of relationship between them. And what's more, there are kind of indirect relationships between Tesco and BP that not only just go through people, but also go through shops and people. This guy doesn't shop at Tesco, but knowing about this guy here might tell you about how close Tesco is to BP, because they're all sort of connected together. So the other thing you'll have noticed, so I'm probably going to get into, some cool stuff. Are we going in the right direction? You're happy? Cool. So we've got this thing here, right? We've reimagined this long, boring list of transactions as this graph, and you'll have noticed that every shop here is intermediated by a customer. It's what we call a bipartite graph, right? So instead of in Facebook, every individual just goes directly to another individual. Here, every shop goes to every other shop, but through a customer, every time through a customer. So you can recast that as this. This is, in fact, exactly that. Right? I just pulled the nodes on PowerPoint and moved them about. So why is that helpful? Because you can then think, well, if I'm just going always through one to get to another, I can just sort of eliminate this. And I can start thinking about, okay, So maybe I am interested in how this customer is similar to this customer, but because I've got tens of millions of these guys and just only millions of these guys, if I understand how Tesco and Asda and BP and Boots and all those guys relate to each other, I can then perhaps in some way infer back how customers relate to each other. I can simplify my problem. So a lot of data science is about getting huge amounts of data and then trying to simplify the problem to make it sort of make sense, or at least to make a computer able to deal with it. So you can get rid of all that stuff and just say in some probabilistic sense, there's a probability of leaving Boots and getting to BP through your customers. You don't care which customers you're going through necessarily, but clearly if you've got lots of customers in common with Tesco, you're sort of more closely linked. That's what this thing looks like. So we've got all sorts of links. You can see this is what we call a fully connected graph. So you can get to any other point, yeah, from each point. So we still haven't kind of really filled out what we mean by how strong the connection is, but we've kind of simplified it down to something we might be able to deal with. This is the good bit. Okay, so we're back to the original graph. So we haven't really addressed what we mean by similarity in this context. We've kind of said, well, we've changed the way we thought about data, and we're thinking about a graph now, and a graph's a bit like Facebook, and Facebook's kind of trendy, so that's got to be good. But what do we mean? So we've kind of created this metric. A metric is just a way of calculating a number that tells you something, right? And this is our thought experiment. So imagine you go to Tesco with a counter. Do you remember those guys where you press a button, every click is a counter, right? And a flag. You go, and it's a big red flag. And you pick a random person at Tesco. You say, look, I want you to take this flag and this counter, click the counter, and then the next shop you go to, whether it's tomorrow or in a year's time, the next shop you go to, find another random person, give them the flag, click the counter, and tell them to do the same as what you've just done. Right? And then I wander off, and I sit in Asda for however long it takes, and wait for that flag to walk in through the door. And at that point, I grab the flag, I grab the counter, and I see how many clicks have been clicked. What is what we've called degrees of separation? So it's like a degrees of separation of social network. Imagine I do that enough times to come up with some sort of average degrees of separation, or expected degrees of separation. Right? This is, in some sense, a way of measuring how close Tesco is to BP, yet you have used the entire graph of every single, the relationship between every single business in the country and all their customers and all their shopping trips in every single pair. You've kind of got the richest expression of how close one thing is to another, which essentially improves your ability to kind of understand the closeness of them. So that's kind of cool, right? We've now, at least conceptually, taken a long list of information, we've turned it into a graph, we've simplified a graph, and then we've had a little thought experiment that said, we can sum this up by one number between each pair, and that number somehow encapsulates everything that you could possibly do with all that information. So what's the problem? I'll tell you. It takes a bit of computing power. In fact, it takes more computing power than you can just have, right? You can't just do it, use a bigger computer, use an even bigger computer and just do it. We'll come to that in a second. And again, this is a lot of the kind of things we do as data scientists. It's not, people talk about algorithms and neural networks and all that stuff, but often it comes down to, that's fine in theory, but how do we get there? And how can we recast? We've already recast our information quite significantly. How can we recast our information in order to make it work, in order to make it tractable? Now, it's complexity. It doesn't look very complex. But imagine this is your starting shop, and in some sense, your guy with the red flag can go to one of three, and of those three, one may be your destination shop, at which point he stops and he gives me the flag. Right? But once he gets to the other two shops, he can again go to one of those three shops, yeah? And he might, actually that looks like he's gone back to the shop he started at. He's probably not allowed to do that. But you can imagine that the possible paths this person could take going through all the 1 million, 2 million shops in the UK or businesses in the UK or whatever it is enormous, right? Because you're going from 1 to 1 million, and then for each of the million, you go to another million. Oh God, so we're at 1 trillion already, okay? And then for each of those trillion paths, right, you can have another million. That's 1 million trillion. That's a big number, right? And we're only on step 3, right? So there's quite a lot there. And 1 trillion is a big number even for big data. So don't worry too much about the first word there. And I'm going to skip over this a little bit. But you can effectively forget about how anyone got to a shop, right? You don't care how someone got to a shop, you just care where they're going to go from there. That's what this Markov word is. So what's the message out of this? You can do some mathematical tricks. And if you're interested in the mathematical tricks, I'm really, really happy to talk to you about it. But the whole point is that in big data, in a big data environment, actually computing it is not trivial, right? It requires quite a bit of thinking about how can I recast it, how can I make this thing work in order to get a number out. So one of the things we can do, as I say, is forget about these things, how the exact path that you've gone in order to get where you get to, and just say, well, I'm going to assume that all I care about is where I am and where I'm going to. And that allows us to reduce it massively, right? Because from here, I go from 1 to 1 million, but at each step thereafter, because I summarize where I am each time, yeah, back to that million, I've got 1 million, in each row going forward. But notice, they're all kind of dependent on each other. That's going to become semi-important. So that thing you've just seen is still problematic, still really problematic. So this is a computer sciencey thing called a kind of a complexity calculation of some kind. But imagine you start off with starting at 1 million different shops, and you need to have all the pairs between those shops, right? So you've got virtually 1 million squared, and therefore you have 1 million nodes at each step. So that's 1 million, million, million. And then imagine you want to go 10, so that's 10 million, million, million. It's still a big old thing. You can't just solve it by going to the cloud, right? That's not going to give it to you. You can do some other cool factorization. This is quite cool. When you look at trees, you can realize that this thing here is exactly the same as this thing here, right? It's just earlier on, right? So once you've calculated this, you never need to recalculate it for any of the things steps back, right? That'll make more sense to some of you than others. But the point again is kind of the tricks. Unfortunately, this is a thing that kind of linearly reduces your problem, like halves it, right? But when your problem is still 1 million, 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 half of 1 million, million, million is still a big old number. And you can eliminate paths. So this is a kind of interesting thing, right? So often, so one thing you can do is you can say, well, of all those 1 million different shops you can go to, it's only going to be 100 that really matter, right? You're going from Tesco to Asda or to Waitrose or Boots or whatever. The big shops are the ones that are going to matter from a mathematical point of view, right? So why don't we throw away the little shops, right? The ones that hardly anyone goes to. Bristol Angling Centre. But from a marketing point of view, that's pretty rich information. The little shop, right, is telling you a whole load more. The fact, if I said you go to Tesco, right, that probably doesn't say a whole load about you, right? But if I say you go to Bristol Angling Centre, that probably tells quite a lot more about you as a personality. So the fact that mathematically you can drop it out without losing very much, from a richness of information point of view, you wouldn't want to do that. It does make the problem easier, though. So this is kind of where we ended up. Kind of threw away the whole of the tree thing. Well, sort of did. And realized that if, again, we kind of recast our problem, and said, well, we don't actually care about the whole tree. What happens if we just sample paths through it, right? Just produce a lot of them, of these samples. Then gradually, what we measure will converge to the real number. And on top of that, so this is a big data thing, this is parallelizable, right? Each of these, as long as you have your transition matrix on each of your nodes, nodes in a cluster, nodes and clusters, clusters, lots of computers all together in a kind of network of some kind, right? You can do each of these independently. So from a big data point of view, that's kind of like an important thing. It turns out this works really nicely, converges quite nicely, and runs miles more quickly and gives you richer information. So that's kind of where I am, pretty much bang on half an hour. And I just wanted to kind of wrap it up and say, well, why have I told you this? You laugh. Perhaps I shouldn't have done. OK, so partly it's because, of course, we're doing cool things at Barclays, and for the small proportion of the world that finds this cool, this is quite cool. Partly because I want you to think about data science as hopefully a really added value part of the digital economy that we're all building, right? And this is not just about people who take some data and chuck it into an algorithm and forget about it and can't really tell you why it's doing what it's doing, right? This is all thinking fundamentally from a mathematical point of view, from a computational point of view, and from a commercial point of view of what this data means, right? And how can we recast it, reimagine it, restructure it in a way that gives us the answer that we need, right? So I guess it's a bit of a cry of help from a data scientist to say, please understand us, right? We are trying to be useful. And then finally, if people are out there who are really interested in this sort of stuff, this is the sort of stuff that we're really interested in. I'm very happy to talk about it.
Thank you very much. There's got to be some questions. I'm absolutely convinced of it. Come on.
Yeah, can I ask, if you build that model all the way through to be able to reach that simplified expression of very complex big data, I mean, that must be dynamic data. There's all sorts of things affecting that. Is that so are those models that you've done earlier on, are they dynamic?
So they are not yet dynamic, but I can use another cool word. So these are monoids. These are commutative monoids. Wow. So apart from the round of applause, right? What that means is that I can run these samples through, and then I can essentially, as this changes, so as what some person shops more at one place than another, I don't need to throw this information away. I can add the information to it. I can just add more of these samples to it, and it will continually converge. As it happens, you would be surprised by how slow people's behavior changes. People don't jump around.
What about an effect like, BP having a terrible PR disaster in the Gulf, and suddenly people, changes people's buying habits maybe?
Yeah. So there are those sorts of things. I guess if we had a really big cluster, we could probably run it in 24 hours. So that wouldn't be a disaster. The interesting thing this does that I talked about earlier is that this is about latent preferences. So the fact that you don't shop at Waitrose in Bristol doesn't mean that you're not a Waitrose in Bristol kind of person. Maybe you live close to it, but your commute takes you out in the opposite direction, right? That's interesting for us, or maybe for Waitrose, right? Because those are the kind of people you might market to, right? We're not, so the challenge here, the challenge with personalization is, the easiest personalization engine in the world is this. You already shop at Tesco. Where are you going to shop? At Tesco, right? I can just take a list of what you do, tell you that that's what you do, and that's actually not a bad prediction of what you're going to do, right? But it's not very useful, is it, right? Because really, if we're trying to get people to change behavior, I want to find things you would do you're susceptible to doing, but that you don't. That's the valuable bit. And people's latent preferences, their unobservable preferences, seem to change relatively slowly over time. The question you ask on that is, how do you know if they're unobservable? Not going to answer that.
In all of this data, if you, rather than looking at the data itself, looked at the sort of unusual bits of it, so if you disregard things that people do every day, they go to Tesco every day, they buy the same thing every day, you disregard all that and just looked at the differences that aren't normally there, would that give you a richer data set to compare with? Or?
Compared to what? Okay, so there's a big thing in the world called anomaly detection, right? Which is fraud, right? How do I detect fraud in a system of some kind? I detect it when something abnormal happens. Question is, what is normal in this case? That's where all the brain ache is. If you can work out what normal is, working out what abnormal is really easy. Now, a big example of this, right, is when you're trying to look at words in text, right? Imagine you have a whole load of documents and you want to know what documents are about. So you want to pick out the words that are important. You don't want the and ah. Well, actually, you probably strip them out specifically, but you may find that certain documents are full of certain kinds of words, and that therefore including them is not very important, right? So, for example, when we looked at a number of shops we were trying to match businesses in Solihull, let's say, the fact that they have Solihull in their name, the Solihull bakery, I don't know, the Solihull hairdressing shop, whatever it is, right? That doesn't really help you work out very much about them in Solihull. It really helps you if you were looking between Solihull and Birmingham, right? But not within Solihull. So you might want to look at those kind of natural language approaches to working out. It's called term frequency inverse something frequency, TF-IDF, right? These are ways of trying to identify what has more informational value in it. That's essentially what you're saying, isn't it? That the Bristol angling shop has more informational value, and if you could, than shopping at Tesco, right? And if you could, in some sense, pre-filter the Tesco out, so you're just left with the Bristol angling shop, you would have improved the information in your data set. Agreed, but it's always identifying what is normal.
Have you got some real life examples of where this has been used and how that personalisation has been used for benefit by the
So this is kind of hot off the press. So this is not, but where are we going to use this? Well, there is a strong hypothesis that you are quite well described by where you shop. Are you do you buy your cosmetics at Superdrug or at Lush, right? Or do you what kind of car do you drive? Are you are you a John Lewis person or a Primark person? There's no reason why you can't be both, by the way. Probably. If you then create that, as it were, the genes in your genome, so each person is described by a list of 1 million different shops that they could or could not shop at. And you remember I talked about Tesco and Asda not just as two different shopping chains, but their location as well. Then that's actually quite a good description in some sense of who you might be. Not a direct mapping, but you can use that as some sort of feature set to put into perhaps some kind of wider algorithm about what kind of mortgage product do you want. Are you going to be buying a long-term mortgage or a short-term mortgage? Are you an affluent person, non-affluent person? But in quite a sophisticated way. In the past, we've talked about segmentations, right? So we create 10 segments, right? Because our brain can't do more than 10, right? Which is fine. And you try and give each one a story, right? And you kind of decide whether someone fits into the story or not. Well, here we're kind of creating segments of size 1. That's the sort of idea, by creating a kind of DNA, a behavioral DNA of each person.
From a privacy perspective, how much can you use this kind of data? realistically speaking, I mean, it would be fantastic if Primark could find out just exactly how many times someone walks out of Boots and goes into their shop versus John Lewis, and I'm sure they would love to get this data from you, but in terms of how actually productive it can be for the kinds of brands you're talking about, or Barclays themselves.
Yeah, particularly since the Daily Mail gave us all a head kicking about 2 weeks ago about this. So there is absolutely no intention to sell this information. This is about us trying to improve our product offering, right? And what does that mean? Well, I think in the past, within these four walls, banks have created a set of products and then used analytics as a way of working out how to ram those products down people's throats, right? Here's a set of products, how can we make them buy them? Here, we're kind of turning it the other way around. How can we use your information to create a set of products that you might actually want to buy, right? That is actually suited to you in some sense. So in that sense, it's about creating new products as much as it is about marketing to individuals. Yes, Primark might well want to see that. I mean, I think the whole privacy thing is a big issue, and my considered and individual opinion is that the problem is clouded by the fact that information is bought implicitly at the moment. So when you go onto Facebook, you get Facebook for free and Facebook gets your data. But it's not kind of an explicit bargain. If we broke that bargain out to say, when you log on to Facebook, you can have Facebook for £10 a month, or you can have it for free and give us your data. That's a bit more of an explicit thing. And I think at that point, privacy, people, certainly in an Anglo-Saxon environment, that will make the world much clearer. We tend to see privacy as a matter of contract or consent. If you go to other countries, for example, Germany, they see it much more as a kind of human rights sort of thing, privacy. And you can imagine, given their history, that's the way they might think about the world. Well, I think the world is, and in fact, interestingly, Google put a huge amount of effort into making their terms and conditions readable, right? And got into massive problems in France, where apparently that just upset everybody. So I'm not quite sure where the terms and conditions are ever going to really be a valuable way of going about them. Finally, Barclays has just produced a product for small businesses. It went live a few days ago, and one of the things it did there was for small businesses, it wanted to be able to give insights to those small businesses about their performance relative to local competition. So it would be like to be able to say, you're a hairdresser in Croydon, you spent £1,000 on electricity last month, all other hairdressers in Croydon averaged a spend of £1,200, right? Or your revenue grew by this and other sweet shops in Birmingham reduced by that, or whatever it was. And clearly privacy is an important issue there, because if there is only one other hairdresser in Croydon, right, publishing that information is giving away, competitive information. And then you also need to understand that from a differential point of view. So if one month you say, here's a statistic about your competitors, and the next month you produce another statistic, and there's been a change of one competitor between the two, one person has shut down or a new person has started up, in some sense you can probably back out from that information. So privacy is kind of a bit of a quagmire, and we are not intending to wade into it.
What would you say the challenges are for the data industry, as if it's an industry on its own, for the next 12 months, say?
Data industry.
You and your team, what's your next sort of...
Yeah. So, I mean, look, I think the big challenge for data, so data as an industry, so I'm going to call it data science. I'm going to rephrase your question because that's what I mainly know about. Data science is this combination of pattern recognition, automation, big data technologies that allow you to do stuff like this. And I think that you can cut the world into data science used by startups. That's, they've got innovation, they don't have scale. And data science used by us, we've got scale, and we haven't really got innovation as organizations. So the challenge over the next, few years at least, will be to see whether the big organizations can get scale to get innovation before the small organizations get scale. And what does that come down to? Well, I think it comes down to one thing that's about big organizations. So I'm talking from Barclays' point of view here, which is, can we overcome our historical bias towards specialization in internal functions such that we can be agile, such that we can integrate and work together in a way that a startup would work together? And from a data science point of view, can we adjust to a more kind of industrialized mindset? Can we start thinking about ourselves in some sort of production sense rather than just guys playing around with data? Because until we do that, I think it's hard to be sure whether chief executives will kind of see the returns. That's quite a meandering answer. It was quite a big question. That was unfair.
It's my event. I can do what I want. Thank you very much.
Anything else?
Any final questions? Oh, there's one.
Oh, quick hand on
How
it
are you
there.
measured as a team? Do you have targets, profit targets, ROI?
How are we measured as a team? So it depends upon what we're doing. One of the things we've been working on is trying to understand who of our mortgage customers is likely to pay their mortgage back next month. So not just a general, somebody's more likely to pay back than another, but who's going to pay back right now? And can we, so for example, in this, we combined your kind of general demographic indicators with events. Could we pick up if someone had a bonus from work, or or it looked like they changed jobs? That might mean they want to pay back their mortgage and move somewhere else, or had made a down payment to a surveyor. So we kind of change those. And for that, it's pretty clear, right? We can see what the performance used to be. We can see what the performance is, and the great thing about the finance industry is you can pretty much deterministically turn that into money. Some of the things are more experimental, and you rely on the indulgence to some extent, of the people paying your wages to do that. So we're much more about delivering stuff that people have faith in, at least at this stage. Delivery, I guess. So my answer is delivery, right? The one thing that you can prove is whether you can deliver something on time.
Thank you very much, Harry.